Welcome back, everyone. Now that we understand the data set we're working with, let's go ahead and jump to the notebook and see how something like linear regression will perform on the data. And the reason we're starting off with linear regression is to show you that certain data sets are just not well suited for certain machine algorithms. And it doesn't matter what hyperparameters you edit in the machine learning algorithms, it's just not well suited for that sort of algorithm. So we're going to discover this when we work with linear regression and even when we try to expand it to polynomial regression. Let's get started by heading over to the notebook. All right, here I am in a notebook, and I've already done the imports for NumPy, Pandas, Matplotlib.pyplot, and Seaborn as SNS. Let's read in our data set that we already talked about. So we're going to say pd read CSV, and underneath the data folder, it is called the rock density xray.csv file. So upon opening that, you should see the data set with the full column names, rebound signal strength in nanohertz, and then rock density in kilograms per meter cubed. What we're going to do is let's just rename those columns to signal and density to simplify things later on. So I'm going to say df columns and call the first one signal and rename the second one density. Okay, so there's our columns. Now let's create a scatter plot. We can do this by simply saying SNS scatter plot. And then I'm going to say x is signal, and my y is density, and my data that I'm working with is df. So we get this kind of sine wave looking thing, and what we're first going to do is see if we can even use an algorithm like linear regression. We'll quickly discover that we can't, because linear regression, even though this is just one feature, it's essentially just going to be able to fit a linear line, a straight line, which doesn't really make sense for something like this curved. So then we'll move on to polynomial regression, and we'll see that also has issues, eventually leading us to more complex models, something like a random forest regression. So for certain data sets, you will need to use those more complex models. And luckily for us, we can easily visualize the issues, but something to keep in mind is you're not always going to be able to visualize those particular issues, which is why we will also be reporting in the test metrics as well, or the performance metrics. Let's begin by splitting the data so we can actually get performance metrics on a test set. We're not going to worry about doing anything fancy like scaling the data or doing something like cross-validation in this particular case, because the data set itself is quite simple. You'll notice signal actually just goes from 0 to 100. So here's the signal, 0 to 100, and then the x-rays are just going from 1.6 to 2.8. So it's already pretty much in the same order of magnitude, nothing too crazy there. So we're not actually going to have to deal with any sort of scaling issues. But keep in mind, for more complex data sets where you have many features with many different orders of magnitude and difference, then you will have to do some sort of scaling. But you'll just have one feature, and then or one feature in signal and one label. So we're not going to need to worry about any sort of scaling issues here. So I'm going to say df, or excuse me, x is equal to df signal. And what I'm also going to do is later on, because this is just a single feature, I'm going to just grab the values and reshape this -1, 1. So I'm going to comment this out for now, and then we'll put it back in. Just I want to show you the error that pops up in case you don't forget to do that or don't remember to do that. So keep that in mind that we will come back to this, getting the NumPy values and then reshaping it. But I do want to show you a really common error that pops up, which means that you should be reshaping that data. So right now, I have my x feature is signal and my y is density. And later on, we'll have to revisit this. Then what we're going to do is say from scikit-learn.model_selection import train test split. And then we do what we always do, say train test split, expand on this. Then I'm going to scroll down a bit until I find this tuple unpacking that I'm looking for. Go ahead and copy that. Going to paste it in here. And I'm going to leave the test size to just be 10% of the data. It's not a huge data set. So we'll say test size is 0.1 or 10%. And let's say random state is 101. So if you just run this with x and y as defined up here in the cell, then it's going to split just fine. However, there is going to be an error when you actually try to fit this to a linear regression, or really any machine learning model in scikit-learn. So let's continue on by saying from sklearn.linear model import linear regression, and then say a linear regression model is equal to an instance of linear regression, Everything so far so good. We've done this a bunch of times already. And then I'm going to attempt to fit the model on my training data. So I pass in xtrain and ytrain. And then upon running this, this is where you get that error. And the reason I want to show you this error is because it's super common for beginners to get this error and then get confused on it. But luckily for us, it actually tells you in quite clear terminology what the error is. So you get all these data points and you're kind of thinking what's going on here. And it actually just tells you to do the following. To reshape your data either using array.reshape -1 by 1 if your data has a single feature, which is our case, or array.reshape 1 by -1 if it contains a single sample. So in our case, we just have a single column of data, that is a single feature. So that's why we have to take the array, that is those values, and then reshape it. If we just had a single row, we would need to reshape it to 1 by -1. So we're going to come back up here, and then I'm just going to say dot values, which means instead of a pandas series, get the actual NumPy array underneath, and then reshape it to -1 by 1, just as scikit-learn requested. So we rerun these cells, and then we're able to fit with no problem. So that's why we have to do .values.reshape, because scikit-learn gets confused thinking, are you sure this is a full data frame or series? What's going on? And you just need to tell it, oh, this is a single feature. And the reason that occurs is mainly the linear algebra that's happening behind the scenes with scikit-learn. It's not able to differentiate clearly on something like this, just this series, whether it's a single row or a single feature, which is why you have to specify with reshape. Okay, so we fit our linear regression model, looking good so far. Let's actually get some metrics off some predictions. So I can say something like LR_PREDS is equal to our linear regression model dot predict, and I'm going to predict x-test. So we notice our predictions are just some values here. Notice they're all very close to 2.22, which is already an indicator that something's wrong. But then we're going to say from scikit-learn dot metrics import mean squared error. We can also import mean absolute error. So we can get mean squared error or mean absolute error. We can do both. And we can begin to compare the mean absolute error of y-test versus our predictions here. Run that, and you can see you're getting a mean absolute error of 0.2. And take a look at the density values again. The density values are going from about 1.6 to 2.8. So it doesn't seem too bad given the range of density values. Your root mean or mean absolute values are actually looking pretty good. It seems on average you're only off by 0.2, and if your mean value is around 2.2 or 2.22, then you're kind of only off by 10%, which may actually be acceptable. So what's the actual issue that we don't get to see just from these metrics? And it's going to be the same thing. If I ask for NP square root of the mean squared error, so I'm calculating root mean squared error right now, I see y-test, and then LR_PREDS, run that, and it's also looking pretty good, 0.25. So we're getting about a 10% error here with 0.2, and there is some deviation, but it's nothing too extreme. So right off the bat, you may be thinking, actually, just a simple linear regression is, on average, performing quite well. And that's really the heart of the problem, on average. So let's actually plot this out. Since we're fortunate enough that we only have one feature, I could easily plot out a predictive model for the signals I expect between 0 and 100. So if I scroll back up here, recall I have this particular plot, which I'm going to copy and paste. And let's go ahead and say plt.figure. And let's make this figure a little larger. We'll say fig size is equal to 12.8. I'm going to increase the DPI a bit, maybe to 200. Run that. And so I can quite clearly see the curve that's happening here. And just based off my performance metrics, I'm getting not super great performance, but also not terrible. On average, I'm performing pretty well. So what's the problem? It's going to become clear if I actually create a plot that tries to predict this output. So what would my actual model look like for a bunch of values between 0 and 100 signal? In that case, I'm going to create an artificial signal range. I'm going to say my signal range is equal to NP arrange 0 to 100. And in fact, let's do this in a cell above. so I can actually see these occurring line by line. So I have my signal range. If I take a look at it, signal range is just an array of numbers going from 0 to 100 or up to 199. And what I'm going to do is I'm going to pass in each of these values into my model. This is the LR model up here. And I'm going to pass each of those values into LR model, and then I will get the predictions. And you'll notice right off the bat, it actually didn't matter what value you passed into your model. It's always predicting something very close to 2.22. Already a strong signal that something strange is happening here. All these predictions are actually looking almost like the same number. You notice it's 2.202 or 04 or 03. So extremely close. That's already indicating that it's actually just reporting back an average. But let's see this visually so we can get an idea of what's happening here. We're going to build out this signal range, a bunch of values here. That way I can actually model this line that is supposedly being fitted to this curve of data. So we have the signal range. Then let's say our signal predictions is going to be equal to my signal preds is equal to my linear regression model dot predict, and then we're going to take in our signal range again. Recall, we need to reshape this, so we're going to say -1 by 1, and then I'm going to run that, get my signal predictions, and you'll notice same deal. It's predicting 2.203 or 2.2204 for almost all these, which means if I were to actually plot that out and say PLT plot the signal range versus my model's prediction, so signal prediction or signal preds, run that, and you can clearly see what's happening here. A linear regression model just cannot fit to this data. It's trying to fit a straight line to something that has these curvature characteristics, which means based off simple performance metrics, it looks like it's doing pretty well. You notice again that the mean absolute error was only 0.2-ish on average. And that's because we're essentially just guessing the average line. Regardless of what signal comes in, we essentially just guess that it's going to be a density of 2.2, which is not what we want. We want something more subtle than that, more nuanced. And how would you actually realize this error if you couldn't plot this out in 2 dimensions? That's why you would have to come back here and take a closer look at your prediction values. And hopefully, if you're astute enough, you'd realize, hey, all these predictions look exactly the same, versus my actual y-test values that are correct are a little more varied than that. They're going to 1.7, 2.2, 1.9, and that's what you would directly compare it to get an idea. Okay, so this was the very first model that we learned about, this linear regression for a continuous label. Coming up next, what we're going to do is try to attempt to fix this problem by going to a polynomial regression model. And we're going to see that also contains a wide variety of issues, which will lead us to move on to things like a decision tree model, a random forest model, or a support vector regression model. So I will see you in the next lecture. We're going to head right where we left off this time into polynomial regression. I'll see you there.